Good afternoon. I'm Avihai. This is Yonatan. We are from the Microsoft Cloud App Security team, and we heard you talk about our anomaly detection that is based on Apache Flink. So, a couple of words about our product, just so you know the problem domain. Basically, Cloud App Security adds a layer of protection over various cloud applications. When I say cloud applications, I mean services like Office 365, SharePoint Online, Google Drive, Dropbox, Salesforce, and various others. These are services you probably use in your own home, in your personal life, and you probably also use for work. Many enterprises in the last couple of years have been transitioning from on-premises solutions to cloud solutions, and they have various issues with this transition. One of the main concerns is security. Basically, users are now using the applications from outside the protected security boundaries of the internal company networks and using protected data from everywhere in the world and using unauthorized devices. Cloud App Security adds a layer above those various applications that give you visibility into the data in the application and also adds protection. So we take our service and we connect to the various cloud applications. We do it using APIs those applications provide. We do it using a cloud proxy that we have, and by analyzing firewall logs from the company. This way you can see all of the users that are present in the application, all of the files in the application, and various activities that are happening in the applications. Once you have the visibility, we can also detect threats that happen in the application. For example, files that are accessed from unauthorized locations, users who have privileges they don't need, or various malicious activities that happen in the service. This is an example of the dashboard of the product. As you can see on the left, you have a list of all the applications that are deployed within this tenant. On the up, if you can see, you have the count of all the users and all the files and various activities that happen in all the applications. And you can see open alerts broken down by various policies. Hopefully, if you deploy the product, you won't have as many alerts as this demo tenant. As I said, one of the data types we have are activities. It's actually our main bread and butter. It's the main data type we store and process in the product. And that data type comes from various sources. It comes from API and proxy, but it also comes from 16,000 different applications. And not only do we have great variance in the applications and the data sources, we also have great variance within each activities. So we've got dozens of different activity types. We've got file download and file upload, file sharing, login user and user logoff. We've got export and import of data from files and from reports. We've got user creation, user deletion, user suspension, adding a user to groups, and these are just some of the examples. We also have common attributes to all the activities. We've got the location where the activities came from. We got the IP address, the ISP that the activity originated from. We got a device that caused this activity, the browser, the operating system, various objects that activity was performed on. For example, if you download a file, that file is an object that we can process, and so on and so on. And because we process so many different data sources, each one of them comes with a different schema, with a different data type, with a different format that we need to process. And each of them have their own difficulties and their own surprises. For example, some of the services that we have give us data up to 24 hours too late, up to 24 hours after that event actually happened. And we need to take that into account. Once we get all the data, we can normalize it within our system to present a unified front to the user. And as you can see on the left side, you've got multiple types of activities. You got file download, login activities, password change. But all of those activities have common traits. They all have a user that performed them. They all have a location that activity originated from, device, etc. And once we present the unified front to the user, once we have a common type for the activities, we can also start to alert on them. Basically, we can see everything that happens in the service, and we can start identifying anomalous activity and even malicious activity, deliberate malicious activity, and basically provide the extra security layer for the product. So Cloud App Security has an out-of-the-box anomaly detection engine that gives you various policies, and we're here to talk about them. So when you start building an anomaly detection policy for cloud activities, you need to build an engine with the basic following flow. You've got an unbounded stream of activities. You go over them one by one and analyze them. You need to extract various security-related insights. Basically, we don't care about everything that happens in the event, only thing that can indicate a compromised account or an attacker. Once you have all those identifiers, you can start and build and maintain a behavioral model for each user. Basically, each user that we see, we build a model of what the user is expected to do, based on the data we saw until now, and based on predictions for the future. And that model is maintained in real time and live during the processing. It's one of the key points of the entire engine. Once we have the model and once we have the live activities that we see, we can start to detect outliers. We can start to detect events that don't make sense, events that indicate that something is fishy, and even actual compromises. Other than that, we even look for known malicious activities that are known to be used to be a sign of attackers. Once we have those detections, we try to cross-reference the detections with previous alerts that we've raised and other user data. So we won't raise many false positives. And also, so we won't get what we call an alert fatigue. Basically, we don't want to alert the admin 1,000 times a day that something weird happened, because then they would stop listening to us. And all of this, from the moment we start ingesting the event to the time we raise an alert, should happen within seconds, because after all, this is a security product and everything should be real time, because we need to stop attacks in real time. That's the basics of an engine. So we need to build something like that from scratch. What do we need? We need a framework that will give us scalability out of the box, because every day we have new customers and new users, and the load on the cluster just keeps on growing. We need a framework that is fault tolerant and gives us automatic recovery, because that product needs to be live 24/7, and we can't have long downtimes, and usually downtimes happen during the night. We need real-time processing, and more important than that, real-time model updates. And as I said, the time from the ingestion until we raise an alert should be as small as possible. We need to raise an alert as quick as we can. We also need to update the job. The job lives forever, and we need to add new features and new detections as we go and as attacks evolve. All of these should reside in state, obviously. So we need a framework that supports massive state, because we have models that we build for every user. That state should be persistent, because machines can sometimes catch on fire, and we don't want it to happen to our data. That state should also be consistent, because our jobs sometimes fail, maybe because of said machine catching fire, and we need to build the state to live forever. And we also need the state to be accessed as fast as possible and in multiple machines at the same time. So we need all of that from a framework. Does anybody know a framework that can do that? So about 2 years ago, we embarked on a quest to find a stateful stream processing framework. We didn't want to build anything in-house, because our idea was that, our belief still is, that the community can build something much better than anything we can build with 20 engineers in-house. We tested about 10 frameworks. Some of them within Microsoft. Some of them are open source. They include Spark stream processing, Apache Samza, Apache Beam, and various others. Most of them didn't have the complex state mechanism that we needed, that Flink provided, which is the reason we eventually chose Flink as the basis of our engine. Our engine, our anomaly detection engine, is named Anubis, after that lovely Egyptian god over there. And it is a single Flink job, end-to-end, that does everything. From ingestion the raw activities, to computing the models, to running the detections, to raising the alerts at the end. One job that does everything, and it looks like that. That's the single job that we have. That's Anubis. And as you can see, it's pretty linear, except from some parts that are more interesting, and we'll touch and we'll talk about them in a couple of moments. Anubis is currently running in production in 8 clusters in multiple data centers. And each cluster has just a single instance of the job processing the data of all the tenants in that data center. Our largest cluster at the moment contains 40 machines and processes 25,000 events per second and holding about 1.3 terabytes of state.
Thank you. Hi. So let's talk about the Anubis pipeline. This is a schematic view of the pipeline. In reality, each box here actually contains multiple Flink operators. So events come in from the source, and the first thing we do is we add features. So each feature is just like a small piece of data that can later be used for modeling and detections. Some features are stateless, like categorizing each event to which activity type it belongs, or extracting some information about the user and attaching it to the event. But some features are stateful. For example, users perform activity. Each activity comes from a certain IP address. So we want to keep track of the IP addresses, and then we want to say we have a feature for how common is this IP address for this user. So this would be a stateful feature with the state keyed on the user. So it would be an operator keyed on the user. And the same thing for IP address can also be for other types of metadata like device. In other places, we want to have features keyed on a user group. For example, the same thing we do for IP address in the user, we might want to have a feature saying how common is this IP address in the user group. So a user group can be the entire organization or some subdivision of that organization, and it's actually a product-derived division into groups. We can't control it, and that's important. So some of these operators are keyed on the user, and some are keyed on the user group. And this keying on the user group can be a potential scalability problem, and we'll get to that. So once we're finished with that stage, we have an event enriched with features, and there are 2 things we want to do with each such event. One is that we want to learn from it, so it's streamed into our models. And the other is that we want to decide whether or not to trigger an alert. I mean, is this event an anomaly, an anomalous event, a dangerous event? And to do that, we have the detections phase, which look at the events and look at the model. So they have an event, they compare it to the most recent model, and we can make a decision whether to trigger an alert or not. Here, we made a decision to separate the models into a different branch in the pipeline and not have them inline. So on the one hand, we do want online learning. We want, if there's a change in behavior, we want to update that quickly in our models to avoid triggering too many alerts due to an outdated model. On the other hand, the model calculation is where we have a potential heavier type of calculation. So we want to avoid having that create backlog and hold up the entire pipeline. So we have the models in a parallel branch, and the models, some of them for each user, we have a model tracking its behavior. I mean, there are several models. This is scalable. We add more models as we go. Some of the models are calculated per user, and again, they're keyed by user. And some of the models are calculated per user group, and then are keyed by the group. Naturally, and this is again, might become a scalability problem. Naturally, if we fed all the models one event at a time, we could, and they would be heavier in terms of calculation, we could create, again, a backlog that would hold up the entire pipeline, and we address this in several ways. So models that are keyed on the user are usually less of a concern than the ones that are keyed on a group of users. Also, some of the models are just lighter, so we don't have to worry about those. Some of the models don't need all the events. For example, one of the models we have learns the typical rate of file download by each user. So to later detect if there's an anomalous rate of downloads. So that model in particular only needs the download events. It doesn't need all of the events. So there's another way to ease the load. However, we do have places where we have heavy calculated models that need most or all of the events and are keyed on a user group, which might become large. And then what we do is we do some sort of pre-aggregation so that these models don't handle every event one at a time, but some pre-aggregated batch of events or pre-aggregated extracted pre-aggregated data from the events that's relevant for that model. Another thing we do here is we key the model part. So the models are keyed either on the user or on the group, and we add to that key also the type of the model. So all the models are calculated concurrently by different subtasks, and this allows us to scale out in the number of models. So adding more models wouldn't hold up the pipeline, but just require more resources. That also means that the models can't be interdependent. They can only depend on the features. And we have a fan-out operator that just duplicates the events to all the models. Now, over here, what we have when we merge the models and the features, we have a co-flat map function operator that gives the latest model for every user and every user group, and then each event is coupled with the latest model at that time, which is usually updated only up to a few events behind that event, which is okay. Then we have the detection phase, which is where the decision is made, given the event, the enriched event with the features, and given the most recent model for that user, do we need to trigger an alert or not? And again, we have several detections, and again, we add the detection type to the key. So this is keyed by user, and we add the detection type to the key, so we can add more detections, and they are calculated concurrently. And again, we can't have interdependencies between the detections. So the detections can only depend on the models and on the features. And everything here is extendable. We have, so the features and the models, our detections are basically a list of plugins. We keep adding to them. In fact, we have several teams all adding features and models and detections to this platform. So if team A is working on a new detection and they're adding a new feature for that detection, that feature is then available for all the other teams, so everyone can use all the features and all the models that we have so far in their new detections. Okay, so let's talk about, we mentioned scalability. We find it useful to define what are the different dimensions in which we need to be scalable and what are the requirements derived from each one. So the most basic thing would be the event rate for the entire cluster. So we need to be able to handle more events as the usage grows for that cluster. And the answer to that is increase the cluster. And that works great. Flink is very well suited for, all we need to do is restart the job from a save point and redistribute the subtasks, increase the parallelism, and it works great. As a side note, we did notice that larger clusters tend to be a bit less stable, so crash a little more. This presents a certain difficulty in scalability in this dimension. Something we don't entirely understand yet. We're working on it. We're in a dialogue with the data artisans guys on it. Hopefully we can mitigate that or completely resolve it. But it's not a crucial issue anyway. The next thing would be the event rate per user group. So a user group can be like an organization or a subdivision of an organization. And if there's a very large organization or a very large group, so a heavy load of events in that group because due to a big number of users can be a scalability problem. So most of the operators in our pipeline are keyed on the user, so they don't care about the size of the group. But there are some places, like I said, some features that need to be calculated on a user group, like tracking what are the common IP addresses or common locations in that group, and some models that are keyed on the groups to learn certain behavior that we want to learn on the entire group. And there we have several mitigations for that. Some of these I talked about in the group-based models where we can maybe process only some of the events or use a LiDAR calculation and stuff like that. But some places we have no choice and we actually perform some pre-aggregation in these places. We do it in the models, we do it in the features, and I can get into more detail about that at the end if we have time. Next thing would be an extremely high rate of events for a single user. So by that I mean like several hundreds of events per second for a single user. Here we have a bigger problem because the entire pipeline is keyed on the user or worse than that. So this is an inherent problem that we can't really get around, and we have no choice except to cap the event rate for a single user. I mean, if we wouldn't do that, then a single user with an extremely high event rate would hold up the entire pipeline, which is serving a lot of users, a lot of organizations. Sometimes a single pipeline serves an entire data center. So one user can hold up the data from an entire data center, and we have to cap the rate for a single user, which basically means we shift the problem to be a product problem. And we can only do that since it's really very uncommon. So it doesn't happen a lot. And when it happens, usually, I mean, always, these sort of users, they're not real human users that are performing such a high rate of activity. Usually there's different sorts of service accounts. So we have some, this is like a product limitation for us. Next would be scalability and adding more features and models and detection. So as I said, we're continuously adding more and more stuff to this pipeline by different teams are writing to the platform. And basically we just key by the feature model and detection, and key by the relevant thing, and so they're calculated concurrently. And like I said, this restricts the dependency between. So no interdependency in features. Models cannot depend on each other, only on features, and detections cannot depend on each other, only on models and features. And then when we add more of them, we just again increase the cluster, like as if there was a higher event rate. And last thing would be the number of clusters. So as usage increases, we set up more clusters at the existing data centers or at new data centers. And here the main issue is to make cluster setup and management as easy as possible to be able to manage more and more clusters. And this is something I'm going to talk about in the next slides. So, okay, we have a Flink job with everything I talked about so far. That was kind of the easy part, right? The really hard part, for us at least, was, I think for everyone, was to get that huge thing to run in production at scale. So I'm going to discuss that in the next few slides. So like I said, we have multiple clusters at multiple data centers. What we do now is we have a standalone setup for the clusters. We just run the Flink services on Linux VMs in Azure. Service installation and configuration is managed by Chef. We have automation scripts, so these are just Python scripts that use the Flink monitoring REST API. We use them for machine setup and version upgrades for the Flink, version upgrades for the jobs, deployment and upgrades. We manage all these scripts. We use management tools like Rundeck and Jenkins. And we are working on a Kubernetes-based deployment to be used in the future. Connectors. So our source of events is Event Hubs. Event Hub is a really good message queue. We're very happy with it. The only downside with it is that there wasn't a ready-made connector for Flink for it, but it wasn't very hard to write one of our own. Event Hub stores about a week of events to allow recovery up to a week back, and each consumer manages its own offset into the event queue, very similar to how Kafka does it. So, and that works nicely with the checkpointing mechanism in Flink, where we just keep the offset of each queue as part of the Flink state. In fact, what we do, we have several input queues, and we keep all their offsets in a union list state. And that allows us, when a job starts or recovers, we take all the offsets and we redistribute them between the subtasks. So this allows us to easily, at every start on every recovery, we can potentially redistribute and address maybe if there's a different number of queues from the last time the job ran, or a different number of subtasks, different parallelism. So it's like seamlessly redistributed on every recovery and every job start. And that's nice, using the union list state. Event Hub also has a monitoring API, so we can get from the Flink job, we can get metrics about the Event Hub queues and log them as part of the rest of the Flink metrics, among them the metric about the queue backlog. And we also use Event Hub as the sink for the alerts the pipeline produces, but that part is really trivial. For the state backend, we use Azure Blob Storage. That was really easy because there's already a ready-made connector, an Azure ADFS connector, which worked great out of the box. The problem with that was that when our state grew to around 1 terabyte, we had a problem with the throughput of a single storage account. The state operations was slow, so saving a checkpoint, saving a save point was slow, and more crucially, loading a checkpoint and loading a save point was slow. So that was became a real problem with recovery and upgrades. So what we did is we wrapped the connector with a multiplexing layer. So we're utilizing several storage accounts simultaneously, and that really got the throughput high enough to be able to easily load and save checkpoints and save points. Upgrades, yeah. So those of you who were at Gordon's talk yesterday, so we can say that every slide in that talk really touched a pain point for us. At every slide we said, yes, we had that problem. So really for us, we have a long living job, okay? So it's been running since the start of the year, and we're still using the same state. We always restart the job from a save point. We have a warm-up of above a month, okay? So we just can't break the state. We need to hopefully we're going to keep the same state for years. But on the other hand, we keep evolving the state. We keep adding features and models and detections, and more importantly, improving the existing ones. So we need to evolve the state, add fields to the to the state objects, etc. What we decided to do, and those of you who were at the talk yesterday about serialization, Gordon addressed exactly why we needed to do it. We just implemented our own serialization for everything based on cryo. So this way we completely control everything. We control the serialization, the deserialization. We add a version number to every object, so we can add and remove fields as much as we like. It's very fast, and we serialize only what we need. We don't need to serialize the schema. We don't need to use reflection, since we explicitly refer to the field in the object serializer. And the downside is that it involves some boilerplate code for each object. So far, it's been worth it. But we're really looking forward to having all the stuff from Gordon's talk yesterday implemented, so we can throw all that code away. But so far, it's working. Okay, monitoring. Flink has great monitoring, but we wanted more. So we wrapped each operator class, each state class, each collector class. The serializers are our own, so we control them. And this gave us a hook for the start and finish of every operator run, every timer run, every state access, every record collection, everything. And we use that to monitor how long everything takes. And we do that globally. We do that per subtask. And we do that per operator key, so per user group, per model, per detection, etc. And it's very helpful in investigating performance. Also, we add metadata using the MDC. We add metadata to every log line with the operator key and the event ID and other useful stuff. All in all, around 15,000 metrics per process that are printed every minute. Everything goes, we use Splunk. It's a great tool. We use it for investigation and dashboarding and alerts if something goes wrong. So here are some examples of monitorings we have of the Splunk dashboards. So this is just low-level stuff, CPU load, thread count, stuff like that. Everything that has to do with save points and checkpoints, operations, when was the last checkpoint, how long did it take, how big was it, etc. Stuff that happen per subtask, record rate per subtask, and how it changes over time. This is some stuff for them from the special metrics we added on top of those of Flink. So the processing time per operator and the net. So this is the processing time, the total one and the net one. So we were able to subtract state access and collection from the running time to get the net running time. So that was very useful for us because we have those hooks everywhere. Specific metrics for time it takes to serialize and time it takes to access the state per operator, per subtask, per everything. This is per user, so these are users just hashed for privacy reasons. So for every user, for a certain operator, which subtask processes it and how long did it take, the record count, total time, average time. Okay, what's next? So we have the Anubis job we presented here today is the most complex job we have. We have another two jobs running and another two on the way. It's a little less complex. Some of them have to do with statistics and analytics. We're really pushing to use Flink for other use cases as well. Also in other groups inside Microsoft, so we're helping other groups deploy their own Flink solutions. We kind of pioneered it inside Microsoft. And we're also working, like I said, on a Kubernetes-based deployment solution in the future. Thank you.
Thank you very much, Yonatan, and thank you for the nice talk. Do we have any questions from the audience?
Hello. Can you talk a little bit about the models that you have? Do you use any machine learning techniques, or how the model evolves when you are using in anomaly detection?
Yeah. So there's only a certain limit to the amount of detail I can go in there, since it's a security product. So, but I can say that our philosophy is to keep every model relatively simple because they're online. In fact, when we do have something really heavy to do, we actually do it offline because there's a limit to what you can do online, but then it has its own limitations because it's offline, it doesn't update quickly. So when we do it online, we do relatively simple things like learn the typical activity rate, like I said, the download rate, learning about common locations and common devices, stuff like that. So there's always a balance between doing things online, then you have heavy restrictions on the performance, and when you have heavier stuff, you need to do it offline, and then you have a problem with updating it quickly. So we have some machine learning online, but it's restricted. I mean, the really heavy stuff happen offline.
Hello, there is a recent Microsoft paper about a system called Quill, and I am wondering whether you looked into that one when you were trying to choose between systems.
We haven't heard about it. Basically, our research was done almost 2 years ago.
Okay.
So it might not have been around there.
Okay, thanks.
Hello. Are you learning this standard location of files you mentioned per user or globally?
So we do both. We do it per user and we do it per user group. So a user group could be the organization. So let's say, for example, for each user, when a user performs an event from a certain location, we can ask, is that location common for that user? And is that location common for that group? And those two features will be considered among a big other number of features, and then we have an edge detection can use these features with different weights to decide if that warrants an alert or not. So some alerts, that sort of uncommon location feature could contribute to them and trigger an alert, and maybe in other scenarios, it wouldn't matter so much.
Any more questions?
I was just curious on you feed events in, and if you have malicious events, you're feeding malicious events into the model, and how you avoid the model being tainted in cases like that.
Yeah, that's a good question. So basically, our approach is, well, I can say it's twofold. One, we assume that the malicious events are relatively uncommon, and that at least the first few ones will trigger an alert. And then product-wise, we kind of say, okay, we trigger an alert on this user. Even if the model is kind of tainted now, we're covered for it. I mean, we trigger an alert, and then, because our alerts, in terms of the product, are kind of like leads for investigation for the security personnel at the customer location. So they're like saying, okay, there's a problem with this user. We might have learned its behavior and not alert further, but now they're investigating it, they're aware of it, so it's not as crucial to keep alerting. So it's not that bad if the model was tainted, and we do forget it eventually. I mean, as time grows, as time flows, the model will be relearned with the normal behavior.
So you've been running with the same state since the beginning of the year, you said. Have you had to deal with any bugs that made it into production that could have affected state that you had to reset or anything like that? I'm not sure if you've ever encountered that sort of thing.
We never have bugs in production.
So we didn't actually corrupt the state. And well, there was something that killed the certain state when we had an instance that the certain state got corrupted. We still don't know why. We had to roll back 24 hours to the last correct save point. But that's the reason we keep periodic save points. We trigger save point every 12 hours just for that occasion. If we corrupt the state, we can always fall back.
And I can also add, we did have sometimes things or mistakes or things that we regretted, not really bugs, but say we designed the state object and when we said we want to do it differently, but since, like I said, we completely control the serialization, it was relatively easy. I mean, design a new one, just be back compatible, and so this complete control of the serialization really gives us flexibility to fix mistakes or even if we discover them too late.
We are running out of time now, so after 10-minute break, we'll continue with next session. However, if you have more questions, Avihai and Yonatan will be here to answer them. Thank you.
Thank you.